Hi, my name is Seokwa, and today I'm going to talk about the integrated power and thermal management with battery degradation for hybrid electric vehicles. This is the presentation outline. First, I'm going to introduce my research background, and then I'm going to talk about the system model and controller design. And I will show you the simulation results, and finally, I will conclude my presentation. Introduction. This page shows the vehicle fuel efficiency requirements by year. Because of limitation of oil resources and environmental issues, the vehicle fuel efficiency regulation has been raised by governments. And then it has brought increased attention to electrified vehicles. Electrified vehicle efficiency is affected by many factors, such as hardware and software. The examples of hardware are vehicle weight, powertrain architecture, and component efficiencies. And the examples of software are control strategies. In this research, we will focus on the control strategy. A key focus of hybrid powertrain control is power distribution between the engine and battery, because they are power sources of the system. One side of the power source is engine. So we can increase the system efficiency by operating the engine at high efficiency points. So many typical power management controllers have been focused on minimizing the vehicle fuel consumption. Another side of the power source is the battery. The battery capacity decreases as the battery cycle increases. And the battery capacity fade decreases vehicle performance. And the battery end of life is typically defined as time when capacity reaches 80% of its initial value. And this requires battery replacement with substantial sustainability costs. Therefore, minimization of battery degradation should be considered for control strategy. Another important factor is the battery temperature, because battery efficiency, safety, and degradation are all impacted by operating temperature. While the vehicle is driving, the battery always generates heat, and the rate of degradation is faster at higher temperatures. And high temperatures bring greater safety risks. The critical point is that cooling the battery requires energy, which is often supplied by the battery itself. Therefore, the battery temperature should be considered for control strategy. This page shows the literature review. Many studies have proposed control strategy for power and or thermal management. There are several examples. First is the power management. Second is power management with battery degradation. Third is thermal management. Fourth is integrated power and thermal management. And number 8 paper and our research consider integrated power and thermal management with battery degradation. The number 8 paper used the convex relaxation for an efficient online optimization. And it includes the battery temperature model. In this research, we extended the battery model to battery cooling system. Therefore, we can capture the thermal management system and which can capture the energy consumption from the battery to perform the battery cooling. Therefore, in this research, we propose an integrated power and thermal management with battery degradation controller. And it can consider trade-offs in short-term efficiency and long-term degradation. Next part is system model. In this research, we consider a parallel hybrid electric vehicle for controller design and numerical simulation. Vehicle system can be represented with longitudinal dynamics, transmission, and battery. The details of the model can be found in our paper. We used 2 battery models to capture associated dynamics and degradation. The equivalent circuit model is used to capture the battery associated dynamics because it is simple and straightforward to represent the battery associated. However, it cannot capture the battery degradation physics. Therefore, the electrochemical model is used to capture the battery degradation behavior. However, the electrochemical model is complex and it requires heavy computational load. So we approximated the battery degradation as a static map to produce a control-oriented model. The battery degradation can be represented with a function of battery SOC, battery current, and temperature. And the figure shows the battery degradation with respect to current, SOC, and temperature. As you can see, the battery degradation increases as charge and SOC and battery temperature increase. Irrespective of this, the general optimization approach can be extended to other battery degradation models and mechanisms. For battery thermal management, an active cooling system is modeled. In the battery cooling system, the energy-consuming components are compressed and pumped. They consume the battery energy. In other words, the thermal management system is powered by the battery, and thus reducing temperature comes at the cost of increasing discharge rate. In the battery cooling system, the battery is modeled as lumped thermal capacitance. And the heat transfer between coolant and battery is modeled using uniform water temperature model. And at the evaporator, the heat transfer between refrigerant and coolant is modeled with parallel flow heat transfer model. Next part is controller design. In this research, dynamic programming is applied for open loop control design. The dynamic programming can solve the optimal controller problem by calculating the cost with all possible state and control inputs and at every time step. Therefore, it can obtain global optimal performance. We designed two controllers for numerical simulation. First one is power management controller. The cost function is the sum of fuel consumption, battery degradation, and final SOC deviation. The system states are gear and SOC, and control inputs are gear shift and engine torque. And the disturbance is power demand. The inequality constraints are operating constraints, and equality constraints are system dynamics. The second controller is integrated power and thermal management controller. The cost function is the same as the first one. However, the system states are extended to battery temperature and coolant temperature. And the control inputs are extended to pump speed and compressor speed. And the inequality constraints and equality constraints are extended to operating constraints and system dynamics, respectively. Next part is simulation results. This page shows the results of power management with and without battery degradation. In the case of without battery degradation, the tuning parameter was selected as 0. The left figure shows the SOC trajectories. The blue line is the result of power management with battery degradation. As you can see, the blue line operates at lower SOC boundary for small battery degradation. By doing so, the power management with battery degradation decreased the battery degradation by 33% at the cost of fuel economy 2.45 miles per gallon. These results can be seen that including battery degradation in the cost function provides an explicit trade-off between short-term and long-term costs. And these results align with the below paper, which considered the power management with degradation, but not thermal management. This page shows the battery thermodynamics impact on the battery degradation. The blue line is the result of power management with thermodynamics. As you can see, the blue line shows the higher battery degradation because of the battery temperature. In summary, the case of with the thermodynamics is increased the battery degradation by 31%. Therefore, we should consider thermal management in the control strategy. This page shows the integrated power and thermal management results. The blue line is the power management, the integrated controller case, and the red line is the power management without thermal management. As you can see, the blue line regulated the battery temperature within desired range. Right figure shows the SOC trajectories. From 0 to 150 seconds, the blue line is lower than red line because the blue line used the battery energy to regulate the battery temperature. And after 150 seconds, the blue line stays slightly above red line. This is because when the thermal management is considered in the controller, the battery is used more sparingly to reduce its C rate and heat generation. These trade-offs cannot be made with conventional control strategies where power and thermal management are not integrated. Therefore, the integrated power and thermal management decreased the battery degradation by 21% at the cost of fuel economy 0.23 mile per gallon. This page shows the tuning parameter impact on the controller performance. The beta star is the nominal value of the tuning parameter. As you can see, the tuning parameter increases. As the tuning parameter increases, the battery degradation is decreased by the fuel at the cost of fuel economy. And the tuning parameter can be selected based on the user score, and the user score can be assessed based on the life cycle analysis for vehicle and battery. Until now, the results of open loop controller have been shown. For closed loop controller, model predictive control is applied as a candidate. The difference between MPC and DP is the prediction horizon length. In practice, MPC cannot use long prediction horizon because of the heavy computational load and the barrier of future information acquisition. In this research, the model is the nonlinear and it requires heavy computational load, and it limits the prediction horizon length. And plus, the charge sustaining constraint limits the SOC trajectories. As you can see, MPC cannot use the broad SOC areas compared to DP. Therefore, our future work would be to reduce the computational complexity and relax the charge sustaining constraint. And for performance validation, the dynamic programming where the tuning parameter is 20 beta star can be compared. And summary, the fuel economy of MPC was almost same as the DP. However, the battery degradation was 44% higher than DP. In conclusion, we proposed an integrated controller for hybrid electric vehicle power and thermal management with battery degradation. And we provide a tuning knob between short-term and long-term trade-offs in sustainability and cost. Our ongoing work is focused on closed-loop control strategies that more closely match the dynamic programming performance. Thanks for your attention. I'd be happy to answer any questions you may have.